let's imagine that in our circuit we have some wire section. And in this wire, I'm going to make a loop. So I'm just going to take the loop, take the wire in our circuit, and I'm going to make a loop. This is going to have a certain effect on the circuit itself. If we want more of an effect, what can we do? Well, I could make two loops right on top of each other. If I want more of an effect, I could make more and more loops. You can imagine maybe something like we had before, where I've got, in this case, 1,000 loops, something like that. That's all we're going to imagine. Just imagine that we've got a loop or a bunch of loops in our circuit. What kind of an effect will that have? Let's imagine I've got the wire and it comes around like this and then continues that way. And let's imagine that we've got a current in the wire in that direction. What is that going to do? Well, we now have the current comes around, the current goes around this way. That current, we know currents in loops create magnetic fields, and the direction of the magnetic field within the loop is, we roll our fingers in the direction of the current. That tells us the magnetic field is going to be pointing out of the page. So we've got a magnetic field within the loop that points out of the page. Well, we've got a loop with a magnetic field in it. What does that mean? That means we have a flux. We have a magnetic flux through the loop. What happens if the current starts to change? What if the current increases? Let's imagine our current increases. What's that going to do? Well, increasing the current increases the magnetic field. Increasing the magnetic field increases the flux. That creates a changing magnetic flux. But a changing magnetic flux creates an EMF. An EMF around the loop that would induce a current, or in this case, induce a change in the current. What direction is that going to do? What direction is going to occur? Well, let's think about this. We know how to use Lenz's law. We have a flux that's in what direction? Out of the page. And that flux is going to increase. So we have a flux out of the page that's increasing. What direction is the induced magnetic field? The induced magnetic field wants to stop that change. It's going to point back into the page. We're going to have an induced magnetic field. I'll do this in blue. An induced magnetic field. Ooh, sorry, I drew it out of the page. Into the page. An induced magnetic field into the page. That is going to induce an EMF in the opposite direction. In this direction. It's going to try and push that current back this way. It's going to try and push the current that way, pull it in this way, and push it out that way. That's going to create an EMF around the loop in the opposite direction, trying to push the current back out that way, pull it in this way. This is a very, very interesting result. And this circuit element is what we call an inductor. An inductor. There is a magnetic field in the inductor due to the current, and that's fine, nothing happens. We don't have an EMF unless the flux starts to change. The flux will change only when the current starts to change. A changing current creates an EMF around the inductor to try and stop that change. You can look at it the other way, and I'm sure you can apply Lenz's law the other way and see what happens if your current is in this direction and starts to decrease, or if your current is in this direction and starts to increase, or if your current is in this direction and starts to decrease. Whatever, what's going to happen is the EMF always tries to stop that change. It's always going to be in the opposite direction to try and stop that change in the current, to try and minimize that current change. What does this mean physically? It means that an inductor kind of adds some inertia to the circuit. If there's a current through the inductor wants to keep that current constant. Having a current is fine. What the inductor doesn't want to happen, so to speak, doesn't want it, doesn't want the current to change. I'll say the word resist, but please don't think I mean as like a resistor. The current resists the current increasing or decreasing. It wants to maintain a constant current. Very, very interesting. How do we describe how strong this inductor works? If it's like one loop or two loops or what? Well, let's think about this. The amount of EMF depends on the change. Remember, the rate of change in the flux. The rate of change in the flux depends on the rate of change in the magnetic field. The magnetic field depends on the current. So it turns out this EMF, or the voltage, across the inductor is proportional to the change in the current. Actually, the rate of change in the current. So delta I over delta T. And remember, it's always in the opposite direction. So we might stick a negative sign in there, but just let's remember that if the current is this way and increasing, the EMF is always going to be in the other direction. We could stick the negative sign in there for Lenz's law. Well, go ahead, but we'll stick the negative sign in there. Okay. Now, how can we make this an equality rather than a proportionality? Well, the number of loops will affect how the flux changes. The area of the loop will affect how it changes. All of those things build in together to describe how powerfully that inductor acts. And we'll put that all into one quantity that we will write as L. L describes how strongly that inductor works. Just like we have a resistance for a resistor, a capacitance for a capacitor, L is what we call the inductance of the inductor. So L is called the inductance. The inductance of the inductor. And we can actually get the units right from here. The units of L will be the units of V times the units of delta T divided by the units of I. All of those put in together give us what we call a Henry. These are my favorite units. The units of inductance are the Henry, which we will write as a capital letter H for short. And just remember, 1 Henry is the same as 1 volt times a second divided by an amp. So 1 volt second per amp. That's a Henry. That's the standard SI unit, so just remember, anytime you put everything into standard SI units, you'll always get the standard SI unit out. Very, very good. Well, let's put one of these inductors into an AC circuit and see what happens. Here is our circuit. Again, it looks a lot like the other circuits. We've got a power supply, V naught sine omega t. Again, the same orientation. This is going to give us a current going up. Now, what's the symbol that we use for an inductor? It actually looks a lot like what an inductor is, a bunch of coils of wires. So, the symbol looks like that. When you're drawing the symbol for an inductor, make sure you make sure it's nice and curly, so to speak, and not just quickly up and down sharp points. If you do that, then it looks more like a resistor. Likewise, when you make a resistor, make sure you make it nice and sharp and not do too sloppy like that, because then it looks more like an inductor. So, a resistor, nice sharp points, straight lines, and inductor, kind of curly lines that overlap each other a little bit. There we go. So there's the inductor. What is the voltage drop across the inductor, just like we had for the resistor and the capacitor? Remember, the voltage will be a drop as we go across, and the voltage will be proportional to L, the inductance, times delta I over delta T. Very good. Now, let's apply the loop rule, just like we did before. Starting over here, you know, it doesn't matter where you start. You can start anywhere you want. You could go any direction you want. You'll just end up with the equation in a different orientation and maybe with an extra minus sign for everything, but you'll get the same result. Doesn't matter at the end. Starting here, going around clockwise, jumping across the power supply, our voltage change is V naught sine omega t. Then coming across the inductor, that's a voltage drop, minus of L delta I over delta T, so minus L delta I over delta T, and that then brings us to where we started, so equals 0. Bring the L delta I over delta T to the other side, divide by L, and we have delta I over delta T equals V naught over L sine omega T. Very, very good. Again, this tells us what delta I over delta T is, but what we would like is to figure out what's the current. What's the current actually doing in this case? Well, let's try and do a similar trick that we did with the capacitor. Let's graph delta I over delta T, which we know has a sinusoidal dependence. So delta I over delta T looks just like the current in the resistor, the charge on the capacitor. Now this looks like this is the change in the current per time for the inductor, delta I over delta T. Let's see if we can figure out what the current looks like. Again, if we think about this, delta I over delta T, that would be the slope of the current versus T graph. So if we graph the current versus T, this is telling us the slope of this graph. Be careful. With the capacitor, we had the graph and we wanted the slope. Now we have the slope and we want to figure out what's the original current graph look like. Well, let's think about that. What do we know? Let's say at this point up here, we're not taking the slope of that. This is telling us the slope. The slope is the largest possible positive value. So I'm going to draw just a little positive line segment to indicate a large positive slope. So large positive slope, I'm going to draw a little positive line element to indicate a positive slope. Over here, a large negative slope. So I'm going to draw a line with a negative slope here to indicate that that part of the graph must be going down. Again, over here, positive slope, little line segment with a positive slope there, and over here, negative slope, a line with a little negative slope there. What about here? Well, this is telling us that the slope is 0, which means the curve must be flat at that point. So I'm going to draw a little horizontal line, a little flat line. Here, again, 0 slope. I'm going to draw another little flat line. Here, 0 slope, another flat line. Now, obviously, I'm kind of drawing these little line segments where I know they'll be able to connect together. If you put them somewhere else, they wouldn't be able to connect together smoothly. And we know we need a nice smooth curve because we have a smooth curve for the change in the slope. So, next one. Here, again, 0 slope, flat line, and 0 slope, another flat line. There we go. Now all we need to do is connect up those little segments so that it's a nice smooth curve. And what do we get? We get something that looks like this. There we go. Very, very good. There is what the current looks like. Notice, what do we have here? What does this look like? What's that shape? Well, it starts out at -1 and then continues on. Well, what does that look like? That's a negative cosine curve. So we know that the current must look like a negative cos. Oh, and then what's the frequency? Well, notice the frequency of this is again the same as the frequency of this. So we must have the same omega t time dependence. So the current in this case must look like minus something cos omega t, and whatever that amplitude is, we can call it I naught. So for the inductor, the current through the inductor has a form of minus I naught cos omega t. Again, we need to figure out what's that I naught. What sorts of things might affect I naught? Well, let's do that just like we did for the capacitor. Again, we can assume that if we increase the voltage amplitude, that's going to give rise to more current. If we increase the voltage amplitude, we would expect to increase the current amplitude. Double the voltage amplitude, double the current amplitude. So we expect them to be proportional to each other. What's the constant of proportionality? We don't know. So again, we'll just call it something. We'll call it x. Well, we already had one X, the capacitive reactance. Well, what do you think this is? This will be the inductive reactance. This is the reactance for an inductor. So X sub L is what we call the inductive reactance. Let's see if we can use some physical arguments about the inductance, about an inductor, and see if we can't figure out what sorts of things might affect the inductive reactance. First, let's remember what was L. L told us the strength, so to speak, of the inductor. And the inductor resisted, and I use that term very loosely, any change in the current. And I said that it was kind of like an inertia for the current. The more inertia for the circuit, the more inertia the circuit has, the more it tries to stay the same, the more it tries to reduce any changes in the current. Well, how might we use that to figure out what the inductive reactance is? Well, let's imagine we increase the inductance. We increase the inductance. How is that going to affect the inductive reactance? Well, let's imagine that I have a mass. Here's a mass, a certain amount of inertia. And I am going to move this back and forth. I'm going to slosh my current back and forth once per second. So I move this back and forth. Okay, and it can move, I can move it a certain amount every second. But now let's increase my inductance, increase the inertia of the circuit. Well, what do I have to do? I need a bigger weight. Now I'm going to move this back and forth once per second. Well, it's much harder. With the same amount of force, I can't move it back and forth as much. It doesn't move as much because it's so much more massive. I would have to apply more force to move it back and forth. But if I maintain the same voltage, the same force, it's not going to move as much. So what does that mean? Well, if we increase the inductance, what happens to the amount of motion of the circuit? In other words, the current in the circuit, I get less current. So I increase the inductance. The current amplitude goes down. If the current amplitude goes down, what must happen to the inductive reactance if this product is going to be the same? Whatever, say 1 volt or whatever. If this goes down, that must go up. So the inductive reactance must go up. Very, very interesting. Could there be a frequency dependence on this? Well, let's think about that. What if we increase the frequency? How will that affect the amount of current, the response of the circuit? Well, let's imagine I've got this weight and I'm going to oscillate it once per second. Okay, and it moves back and forth. Now, without changing the force, I oscillate it, say, 5 times per second. I cannot move it back and forth as much. If I try to shake it back and forth 5 times per second, I can't move it all that way. So what happens? The amount it moves must be less. The response is less. I must decrease the amount of current. If I'm trying to slosh it back and forth faster, the amount of current that's going to end up moving will be less. So, if we increase the frequency, the current amplitude must decrease. Again, if the current amplitude decreases, that must mean the inductive reactance must increase. Excellent. It turns out the inductive reactance does not depend on anything else other than omega and L, and we see that it must increase for increases in omega and L, and it turns out the result is then that the inductive reactance is exactly proportional to both. It is just equal to the product of omega and L. And once again, let me just mention, what are the units of X sub L, the inductive reactance? Again, same as the units of capacitive reactance and resistance, all ohms. Very, very good. Let's just recap what we found for the inductor.